Question 10 then, and we're looking at something called the empirical formula of substances. So empirical formula, to give it its simplest definition, is what we call the simplest whole number ratio of elements or atoms of elements, so of atoms of each element in a compound. Okay, so what we see at the moment on the screen is we've got the chemical formula of this substance here, so C8H16. That tells us we've got 8 carbon atoms and 16 hydrogen atoms in a molecule of that substance. Okay, now empirical formula, we want to know what the simplest ratio of those numbers is. So I'm going to write out C8H16. We want to figure out what the simplest ratio is of 8 to 16. Now both of those numbers can be divided by 8 to give us a whole number, and that will give us a ratio of 1 to 2. So therefore, our empirical formula we write in a similar way to a molecular formula. It will be C1H2, but remember we don't need to write the 1 in there because the 1s are implicit. So if you've got CH2, well done, that's worth a mark. Now using the same logic, we can do the same thing again for this one, so P4O10. Both of these numbers can be divided by 2 to give us P2O5. That ratio, 2 to 5, cannot be simplified any further to give us whole numbers, so therefore P2O5 is the empirical formula. 1 mark for that. This next one, this is a substance called potassium dichromate. You don't need to know that, but you just need to know how to figure out what the empirical formula is. Now, the ratio here is 2 to 2 to 7. Now, because 7 is a prime number, it can only be divided by itself and 1, as is 2, it therefore means that this ratio cannot be simplified any further. So therefore, the molecular formula, or the standard formula of this chemical, is exactly the same as its empirical formula. So K2Cr2O7 is also the empirical formula. So well done if you spotted that. Finally on A, part 4, we've got C6H6. Now, hopefully it will be no surprise to you that both 6 and 6 can be divided by 6. So if we divide both of those numbers by 6, we end up with C1H1, but we don't need to write the 1's in. So our empirical formula is just CH, and you pick up a mark for that as well. So that's how to deduce an empirical formula from the chemical formula of a substance, but you might be asked to do it in a slightly different way. Okay, you might be given some information about a chemical reaction that's happened. So let's go through this example. Now this would be worth 3 marks, and you have to show your working here, because if you don't show your working and you just write the answer, you won't get the marks for this type of question. So it's telling us here that 11.7 grams of potassium was reacted with 4.8 grams of sulfur to form a single product. We want to deduce or figure out the empirical formula of the product of this reaction. So we want to know what the simplest whole number ratio is of the atoms of each element in the compound formed. So what we do here, we set our answer up like a table because it makes our working really clear. So potassium's chemical symbol is K, sulfur's is S, so I'm going to put those in my table like that. And then I'm going to ask myself a similar question to what I've asked before. I'm going to ask myself, what's the mass of Arthur mole rat? So Arthur is a way of remembering that it's the relative atomic mass of these substances that we're interested in. Now, the reason it's atomic mass is because we're looking for, remember, the empirical formula being that ratio, simplest ratio of the number of each type of atom. So that's why we use atomic masses here rather than any formula masses. So let's work our way through it. So have we got the mass of potassium? Yes, it's 11.7 grams. Have we got a mass of sulfur? Yes, it's 4.8 grams. And now what we're going to do, because we've got those bits of data, is we're going to work our way down both sides of the table simultaneously. So the relative atomic mass of potassium, K, we're given in the question, it's 39, but remember you could find it on the periodic table if you needed to. And then for sulfur, it's 32. We want to do these calculations to find the number of moles, so we can do 11.7 over 39, 4.8 divided by 32. Again, that's why we're laying it out like this. If in doubt, find the moles. 11.7 over 39, you do that calculation, you get an answer of 0.3. You do 4.8 divided by 32, you get 0.15. So now the last step is to find the ratio of these two substances to each other. And once again, as I've said, some of you might be able to look at these ratios, these number of moles, and think, I can figure out the ratio from there, no problem. But if you're not sure, just do both of these numbers and divide them by the smaller number. So 0.15 is smaller than 0.3. So if we do 0.3 divided by 0.15, we get an answer of 2. And if we do 0.15 over 0.15, we get 1. So therefore we end up with a 2-to-1 ratio, but that isn't our final answer because that's not how we write an empirical formula. We have to write it in the form K2S, and that is our final answer. Now this would be worth 3 marks. You get your first mark for calculating the moles of each substance, so 0.3 and 0.15. You get your second mark for deducing the ratio as 2-to-1. And you get your final mark for getting the final answer correct, K2S. Now, the other nice thing about this question is that you can actually check your answer using the periodic table because potassium is in group 1. So when it forms ions, it loses 1 electron to form K+ ions. And sulfur is in group 6. So when it forms ions, it will gain 2 electrons to form S2-. So we know that to balance that 2- charge of the sulfide, we will have 2 potassium ions with that positive charge, so it makes it checkable. You can check and say, oh yeah, that does make sense. So that's a thing that you can do, provided you haven't got any transition metals from that middle block of the table in your answer. So that was 10 part B. We'll now look at a similar example, 10 part C, where the ratio is slightly different. So this time we've got 26.88 grams of iron. So iron has the chemical symbol Fe. And we've got 11.52 grams of oxygen. That's got the symbol O. And we're going to write in our details here. What's the mass of Arthur mole rat? So remember mass, we've got 26.88 grams of iron. We've got 11.52 grams of oxygen. And then we're going to work our way down both sides of the table. So the relative atomic mass of iron, Fe, is 56. The relative atomic mass of oxygen, which is O, is 16. And then we find the number of moles by doing our division. So 26.88 over 56, that gives us an answer of 0.48. 11.52 over 16, that gives us an answer of 0.72. Now we find the ratio, we divide both of these by the smallest number, which in this case is 0.48. If you do that, you'll notice you get an answer of 1 to 1.5. That's not the simplest whole number ratio though, so we need to multiply both of those numbers by 2 to get the simplest whole number ratio, which gives us 2 to 3. So we've got a 2 to 3 ratio, but of course that's not how we write our answer. We will write it as Fe2O3. Once again, the 3 marks for this question, you'll get 1 mark for the number of moles for both substances. You'll get 1 mark for the 2 to 3 ratio, and then the 3rd mark for getting Fe2O3. Finally then, part D, a very similar question, but this time there's an extra little add-on bit, which is to find the molecular formula of the compound in question. And we're given a bit of extra information in the question as well. We're told the relative formula mass of the compound. That's going to come in very handy later. But the first thing we need to do is deduce the empirical formula of a compound that contains 8.40 grams of carbon and 1.40 grams of hydrogen. So it's no different from the questions that we've been doing before. So we put our carbon in, we put our hydrogen, we ask ourselves the question, what's the mass of Arthur mole rat? The mass of carbon is 8.40, the mass of hydrogen is 1.40. We need to divide that by the relative atomic mass to get the moles. So the relative atomic mass of carbon, we're told here, is 12. The relative atomic mass of hydrogen is 1. We do those divisions. We get as our answer 0.70 and 1.40. If you get to that stage, you get 1 mark. Find the ratio, divide both of these by the smaller number, which in this case is 0.70. And that gives us a 1:2 ratio, which means that the empirical formula is equal to CH2. Now that would be worth 3 marks. But now we need to deduce the molecular formula of this compound, and we know the empirical formula is CH2, and we know the relative formula mass is 70. Okay, so what I've done so far, that's part 1. Now I'm going to do part 2. So if my empirical formula is CH2, the best thing I can do here is figure out what the relative formula mass of this bit is here, this ratio. So carbon has a relative atomic mass of 12, and hydrogen, we've got 2 of those, and that's got a relative atomic mass of 1. So if I do 12 plus 1 plus 1, I get a relative formula mass for CH2 of 14. Now here's the crucial bit. We know that the relative formula mass of the compound is 70. So I want to find out how many times 14 goes into 70, because that's going to tell me how many times I need to times my empirical formula by to get my molecular formula. So to do that, I'll do 70 divided by 14. That gives me an answer of 5. If you've got that far, then you'll get a mark. So therefore, if I'm going from CH2 and I'm timesing the number of carbons by 5, it's 1 times 5, which is 5. And I'm timesing the number of hydrogens by 5. We had 2 before. 2 times 5 is 10. And that is your final mark there for this question. So the key thing to note there for the second part is to find that relative formula mass of the empirical formula and find out how many times it goes into the actual relative formula mass. Now, the nice thing here is if you calculate this value and it doesn't divide exactly into this one, then it means you must have made a mistake somewhere. So it is worth double checking your answer afterwards. Similarly, you could also double check with this final answer whether it does add up to 70. So we've got 5 carbons, so that's 5 lots of 12. We've got 10 hydrogens, that's 10 lots of 1. 5 times 12 is 60. 10 times 1 is 10. 60 plus 10 is equal to 70. So we've double checked our answer. We can be sure it is right. And that's pretty much everything that you need to know about empirical formulae.